So I'm going to start recording. So let's go ahead and talk about what we've got here. So this is week 8. I'll go through and put in the index tree. I need to fill out the other stuff. Like I said, this is week 8. Recursion is due at the end of the week. I'll go over that in a second. But start getting ready to watch the tree videos. The one warning I'll give you is that you'll notice that there's only 8 videos for the binary trees, but the second one is a bit of a doozy. It is the only time I am giving you a hour-long video. Now, why am I doing that? Ooh, wow, look at that beard. The reason I'm doing that is because it was the one time, basically, I managed to, every single time I have tried to do an explanation of trees and their definitions and their properties, the non-coding stuff about trees, it has taken an hour and a half. Somehow in this lecture, I managed to do it in just an hour. It is the best lecture I've done for this one in terms of time. So I'm like, I've tried to break it up into segments and make it more digestible. It just doesn't work as well. I'd be condemning you to doing more watching. So this is the theory stuff. It's an hour long, but I managed to get through it all, basically through all the things. So sorry about that, but just giving you a heads up. And then the rest of it, the actual building a binary search tree from scratch, is the coding part of it is here. This is all very relevant for that homework. Most of the homework is just simply implementing that with a twist or two. Okay, the thing that gets most students is that the individual items in the tree contain other data structures. Like each node contains a list in it. So it's a data structure that contains data structures. But the way I like to think about that is when you're dealing with it, the metaphor is a filing cabinet. You open up a filing cabinet, which is an outer structure, and the inner structure is filled with folders. Okay. So anyway, going back to so that will be that. Heaps are there as well to watch, but notice that the heaps, while they have their own thing, they don't have a quiz, they don't have homework associated with it. The reason being is I just don't have time to fit in a second homework. I don't have time to do that, but it will be on. But things from this section will be on the exam. Specifically, if you'll note over here, it says, "Hey, draw a heap." Heaps look a lot like trees, only they have a completely kind of different structure. I mean, they look a lot like trees. They just get built different. And then the other bit of it is Huffman coding, which is one of those topics that I love because companies that do interviews are always surprised to find that students have found out about Huffman coding. So you should be watching the tree videos this week because technically week 9 you should be watching the heap videos. Huffman coding is just simply, it is basically learning about compression, like how do you create zip files, in other words. This isn't necessarily the algorithm that will be used for a zip file, but it gives you an idea of how these things work in practice with lossless compression. In other words, we can compress something and not lose any data, which is important for text because you don't want to miss any of the words. Stuff like audio, MP3s and video like MP4s, we can do those kind of compression. We call that lossy because you can throw out a bunch of the data and you can still have an enjoyable experience. The human ear doesn't necessarily understand that a lot of data is missing, and then the human eye, if you're sitting far enough away from the screen, given the video format, it's going to look just as clear as the high resolution one. Or not just resolution, but like a higher bitrate one. So yeah, watching those videos. Let's see. So now with regards to the homework with the 8 queens. So in the folder for GitHub, you will find this file. To get there, by the way, just if you're watching this video later, to get there, right, this has always been there. You just simply go over here to GitHub under the important links. And this will bring you to this repository. And you can go to data structures, destruct, and then you can go to recursion or to whatever you need. A lot of this has code that I did in class. in part of the lectures. But if you notice over here, I have my 8 queens code, which I did a number of years ago. And what we've got over here is kind of the, let's go ahead and look at it raw. We've got a bunch of different pieces of it. So first off, we have our solve function. And this is the way that your solve function should look for both, very similar to this for, your solve function should look like this for the 8 queens. It'll look somewhat similar to this for Sudoku. But we'll take a look. So again, for the solve method for the board, we're going left to right on the board. We're going from the leftmost column to the rightmost column. And so if the board is greater than or equal to the board.length, that means that we've gone left to right, and guess what? We filled out everything. We are now out of bounds, so return true. We finished the puzzle. The only way we can get to that point where we are out of bounds is if we've placed a queen everywhere and we didn't run into a dead end, okay? The default is that we have to return false because we need to backtrack, because we did not get to an answer. So the for loop looks like this. For every row and row is less than board.length, so for every possible row choice, 0 through 7, if it's if is valid board row column, if it's is valid to put a queen here on the board row and column, I don't have to provide a fourth argument here, but in Sudoku, I will have to provide a fourth argument because I'm simply asking if this is a 0 or 1 already there. Oh, sorry, not a 0 or 1. I'm asking, is that a safe place to put a 1? And if it is, I put a 1 there to represent there's a queen, right? This is why I say, hey, you should, when you do your check, when you first write it, you should write your isValid function and just simply return true, because you want to make sure the recursion's working first before you try, getting logic. And so you'll get a top row filled with queens, which is obviously not a correct answer, but it's a working program. Okay? Doesn't mean it's working correctly, it's just working. Then here is the recursion. If we can solve, so that's the same function, the board, specifically if we can solve the next column for the board and that returns true, then we're going to return true. Okay? So if the next column reports that they got to the end, then we're going to report that we got to the end. And so whoever called us will then report that they got to the end. Who will then say, whoever called them will report they got to the end. It's a kind of a chain of trues once we hit the final column. If, however, we get a false, that means that I call solve, it goes through all this stuff, and then it returns false, meaning it got to a dead end. So if that's the case, I'm not going to return true. I'm going to pick up the queen that I just put down. And then I'm going to go on to the next row. If I go through all the rows and I wasn't able to put a queen down and keep it down there, then that means that this is a dead end. This branch should be terminated. So I'm going to return false, and that will tell whoever called me they need to move their queen. They need to pick up their queen and then go to the next row in their column. All right. Main function will look something like this. Here's a blank board, a bunch of zeros. You could also use, underscores and Qs, right? You could use characters instead of integers. It doesn't matter. I'm not picky. Solve, and then for every row in the board, print out that row to print out what we're doing. So, all right. So is valid. Basically, there's 3 things you need. If you remember from last week, from before spring break, basically there's 8 directions a queen can capture, but you don't have to check all 8 possibilities to see if there's a queen in there. Because we're moving left to right, we know that there's never going to be a queen to our right? So we don't have to check any of the 3 directions going to the right. That would be the upper left, the middle, and the lower left, right? Similarly, since we're working column by column, we know that there's never going to be any queens above or below me, right? So that just leaves this one, the upper left, to the left, and then down to the left, right? Which I call going to the left is row valid, right? So what I would do is if not rows valid, or
if the upper is not valid or if lower is not valid, return false. So I typically, rather than trying to do it in three functions, in one function, I make one function that calls three other functions because I have three parts, right, to check. And I can work on them independently. So here's that first part, checking if the row is valid. If the row is valid, I'm going to assume that it is valid until I bump into a queen. If I bump into a queen, I'm going to return false. And so what I do is I'm checking if row column minus I has a queen. Why column minus I? What I'm doing is I'm starting at row column and I'm going to radiate outwards from it. And this should be the structure you use for going up to the left and lower to the left. And so notice over here I start with 1. Why? Because there's no need to check. Because if I check row column, there's going to be a queen there. Well, not really because I haven't put it down yet, but that's where I want to put the queen. So we know there's not a queen there. So, and then I'm checking column minus I greater than equal to 0. That's when I'm stopping. That's column minus I, that's whatever column I'm in, and then minus I will keep moving to the left. Once this is false, I'm going to be in -1 territory, which would be out of bounds, so that seems like a good place to stop checking. And so I get to keep increasing I. And notice that basically here that this condition can, again, this is just kind of show you that the condition here can be whatever you want. And that's important for the checking the upper left and the lower left, because you'll want to do the same thing, just kind of but both the row and the column will be changing, so you'll want it to be a compound statement, like row minus I and column minus I, or maybe it's plus for one of them, right? So, and then here I'm just simply checking if radiating outwards, if I find a queen, return false. Breaking it up like that is also a great way to solve the Sudoku puzzle problem. But again, if you need this as a reference, rather than having to furiously jot this down, again, just come over here to the data structures, hit GitHub, and again, you can just go to destruct and recursion, and I've got so much stuff in here, it's very interesting, you can see. So, yeah. The next homework will be the tree homework, which you'll be able to use quite a bit from the, let's see, where is that? Is it B? Trees. It's not red black, I don't think. Where is my trees? I mean, Spring 2017 has trees, so you can look at that, and you can go through and see, oh, here's all the tree stuff that I've done. For trees, I do use the E extends E comparable, which just simply allows, which is important because trees, the way binary trees work is that you can only really use them on sortable data. And so this enforces, hey, these things need to sort. All right. So yes, this should hopefully help you get, so what I've showed you should hopefully help you get started. Again, you can find it in recursion. The last thing I want to say is an aside I made, but I want to kind of just forcefully make it now. We have learned, so we've learned 3 data structures, sorry, not data structures, big O notations so far, okay? And recursion introduces a 4th one, right? So we've learned constant time, linear time, and quadratic time, right? The work is always the same. This is the work increases proportionally to what I have. In other words, if I double the amount of input size, I double the amount of work I have to do. If I add 10 times the amount of 10 times the amount of items, I have to do 100 times the amount of work. Recursion often lets us see this runtime. Log of n, which is scary because it's got log in it. Specifically, and by the way, when we do big O notation, we typically don't care what log we're using, but typically
if we're in computer science context, we're talking about this, LGN. There's some notations that are very specific, that we make very specific assumptions about. When you see a log, typically, if you're in any context but computer science, you're assuming base 10. If you see it in computer science, you're assuming it's log base 2. But sometimes you'll see in computer science written with two symbols, LG, to assume it's base 2. So that's why you might see that. The other one you're more familiar with is the natural log, which is log base E, which is a weird number, but it's useful. But we typically assume, but Big O doesn't care. Log is log. And what this means is that basically every time you make a choice, you're halving the amount of search space you have, or you're splitting up the search space dramatically. If I double the amount of items I have to do, this says if I double the amount of items, I have to do one more unit of work. So it grows very slowly. It grows, but very slowly. This is because, again, as I've mentioned, you've been taught logarithms fairly, in a fairly annoying way, with basically having to do with like reciprocal relations between, like, basically we say, hey, some a to the bth power is equal to c, right? And then we would say log of base b of c is equal to a, right? And that has A, B, C's and makes you want to go back to kindergarten to sing those, because that seems a lot more preferable. Embarrassing yourself that way seems a lot more preferable than having to deal with this. I'm here to tell you that basically for computer science, you don't need to worry about that mathematical relation in this context when we're talking about data structures. What we care about is what the log operation does to a number, not the relationship. And what the log operation does is tells you how many times you can split it. A log base 2 of 64 tells us how many times we can split 2 in half. In other words, we're asking how many times, so let's just do that actually. So 64 can be split into two 32s, right? Why am I caring about how many 2s it can split into? Because log base 2 splits, it's halves. If it was log base 3, I'd be trying to see how many times I could split it into thirds. If it was log base 4, I'd be seeing how many times I could quarter it, okay? So 64 can be split into half by splitting into 32s. A 32 can be split into 16s. A 16 can be split into 8s. 8s can be split into 4s. 4s can be split into 2s. And those 2s can be split into 1s, and we can't split 1s anymore. Okay, so let's count that up. We have 1 split here, 2, 3, 4, 5, 6 splits. So log base 2 of 64 is 6. We can split it in half 6 times. Okay, and if you check your math, right, 2 to the 6th is equal to 64, right? And if you played, and if you're into video games, you know that, or really into the weird angle of video games, you know that 2 to the 8th is 256, because 255 is like the maximum value for in a lot of video games. Half of that is 128, and half of that is 64. 2 to the 6th would be 64. So we see that. So this splitting operation is a good way of kind of looking at it, because when you're dealing with binary search, right? And this is why we look at it this way. When you're dealing with binary search, where basically you've got this sorted array of numbers, right? It's just sorted, and we want to search to see if an item is in this array. Because it's sorted, we would start in the middle, and if it's less than, we would go to the left. If it's greater than, we would go to the right. If it's less than, we can throw out this entire side, which is half that amount. And then we would look over here and throw out this side, and we've halved again. We've halved it and halved it again, right? So every time we're making a choice, we're splitting the amount of search space we have in half. Make sense? So that's why and again, a logarithmic operation asks, how many times can I split this in half? Well, the amount of search space over here is getting halved each time. That's why it's a logarithmic operation.
So we see this one a lot. So this leads us to the runtime that we'll see later when we talk about sorting, which is O of n log n. And what this means is that basically we're going to split this problem into in half n times. We're going to split, sorry, not split in half n times. We're going to split in half log n times, right? So, and each of those splits is going to take O of n to process. This may seem like a lot, but remember, this grows fairly slowly, right? So if you've got 64 items, we're going to split it in half 6 times, and each of those is going to take around 64 steps, which is a lot better than O of n squared, because O of n squared would mean we would have n, we'd have n operations done n times, 64 times 64, which would be 2 to the 16th, right? Not 2, sorry, 2 to the 12th, 2 to the 12th. Which at that point, I'm not going to bother trying, once we're doing that, I'm not going to bother trying to do that anymore. I'm just going to leave it as 2 to the 12th, right? Because, all right, so trees are great like that. An example, or another example of how that can come about is, besides splitting up into layers, is a very simple sorting technique called tree sort, which you'll see later once you understand trees. But the idea here is that adding or removing to a tree always takes, on average, log n time. So every item we add n items. Each addition operation takes log n time. Then we print the tree, that takes n time. So it's n log n, because we did n log n operations plus an n for the printing. So overall runtime would be n log n, big O n log n. So it's part of the reason that one's that way. But again, we'll get into sorting algorithms later. All right, so I've been droning on long enough. So